Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Homework, Lecture 105. Number 1. In class, I showed that the electric field at m, a distance r from the origin of a dipole p oriented along the z direction, is E sub z equals p over 4 pi epsilon naught times the quantity 3z squared over r to the fifth minus 1 over r cubed. Show that this equation can be written as E sub z equals p over 4 pi epsilon naught times the quantity 3 cosine squared minus 1 divided by r cubed. Okay. This is not too bad. So basically we just need a substitution. And so what we're going to substitute, we'll draw a little diagram here. Here's the point P. Here's the distance R. This is the angle theta. This distance is Z. And so the cosine of theta is equal to Z over R. This means that E sub Z is equal to P over 4 pi epsilon naught times, I'm just going to kind of pull things out, right? 3 over r cubed times z over r all squared minus 1 over r cubed. And so you can see here's where we're going to do the substitution. P over 4 pi epsilon naught times 3, and we'll just replace z over r quantity squared with cosine theta squared minus 1 all divided by r cubed. And that's it. Okay, number 2. Calculate the x and y component of the electric field for a dipole P. The z component is shown in problem 1. Recall that the potential was shown in class to be V equals kappa P z over r cubed, or P over 4 pi epsilon naught times z over r cubed. Okay, so I did the harder component in class, and I saved the easier components for the homework. We'll only need to do one of these, and you'll see why in just a minute. So let's do the x component. E sub x is going to be equal to minus dv over dx, which is just going to be minus p, the z just comes right out because there's no x dependence in it, 4 pi epsilon naught times the partial derivative with respect to x of 1 over r cubed. So we'll just write that 1 over r cubed minus pz over 4 pi epsilon naught. And now let me expand out that r cubed and write it as x squared plus y squared plus z squared to the 3/2 power. So now we just need to take the derivative of this. And so that's going to give us, let's see, minus pz over 4 pi epsilon naught. We'll keep that. We'll get a minus 3/2. This is supposed to be a minus because it's 1 over r cubed. So we'll get a minus 3/2 from the derivative. Then we'll get our x squared plus y squared plus z squared to the 3/2 minus 1. I'll just do minus 2 over 2, and it's minus 3/2 minus 2 over 2. And then inside, the derivative is going to be just 2x times 2x. And all of that reduces to 3pzx over 4 pi epsilon naught, 4 pi epsilon naught, and minus 3/2 minus 2/2 is just going to be minus 5/2, so this is r to the fifth. And so there's that component for x. Now, you could redo this for y, but you can kind of see what's going to happen. Instead of taking a derivative with respect to x, everything will be the same, except we'd have taken the derivative with respect to y, and we'd get a 2y instead of a 2x. And so E sub y is just going to be 3pzy divided by 4 pi epsilon naught r to the fifth. Okay, number 3. The x and y components of the electric field for a dipole oriented in the z direction can be combined into a single transverse component. And the E sub transverse as a function of r and theta is just equal to the square root of E sub x squared plus E sub y squared. And so we want to derive an expression for this in terms of r and theta. Hint, cosine of theta is z over r. Sine of theta is the square root of x squared plus y squared, all divided by r. Okay. This is actually pretty straightforward, even though it sounds like it's terribly complicated. Let's just write out the transverse component as E sub x squared plus E sub y squared. And we should have kept the answers from before, from problem number 2, because we'll need them here. This is going to be equal to 3pz over 4 pi epsilon naught r to the 5th times the square root of x squared plus y squared. That's just from problem 2. Because we have the E sub x component was just this times x, and then the E sub y component was this times y. But if we square all of that, we can always pull out this term here, but we'll be left with the x squared and the y squared underneath the square root sign. Now let's observe that z over r is just the cosine of theta, so let's pull one of those out, 3p over 4 pi epsilon naught, and we'll have a z over r. That's going to be our cosine of theta, but we'll also have this term here, x squared plus y squared over r, and we've got 2 r's. We need one more r in here, so we'll do 3 more r's, r cubed, because we had r to the 5th originally. So r cubed, 1 over r, that's r to the 5th. Now we'll just substitute it in for this. This is going to be cosine of theta. This term is going to be sine of theta. We get 3p over 4 pi epsilon naught times the cosine of theta times the sine of theta, all divided by r cubed. And this will be our perpendicular component as a function of r and theta. There. Number 4. Using the simple ball and spring model from class, calculate the dielectric constant for hydrogen at STP. Recall that the ionization energy for hydrogen is 13.6 electron volts. Compare your result with the experimental value of the dielectric constant for hydrogen is 1.00026. You may use an alternative units for the h bar, constant of h bar equals 6.582 times 10 to the minus 16 electron volt seconds. Okay. So number 4. So recall from class that omega is equal to E over h bar, and we'll go ahead and use those alternative units. We'll put in 13.6 electron volts, and we'll divide that by 6.582 times 10 to the minus 16 electron volt seconds. Remember in class I converted electron volts to joules and used h bar in joules, and the appropriate unit for joule. Here we can use a more convenient unit that's got electron volts built right into it. We divide these two, what do we get? We get 2.066 times 10 to the 16 hertz. Okay, so now we have omega, and so just recall the formula from class. It's going to be 1 plus the dipole density times the charge squared divided by epsilon naught, mass of the electron, and then of course this frequency squared. And so if we plug all these numbers in, what do we get? We get 1 plus 2.69 times 10 to the 25 per meter cubed. That, by the way, just comes from the usual 22.4 liters per mole for gases at 0 Celsius and standard temperature and pressure. Then we put in the charge for the electron, 1.602 times 10 to the minus 19 coulombs, which will be squared. We'll divide this by 36 pi times 10 to the 9 coulomb squared per Newton meter squared. And then the mass, that's just epsilon naught. And then the mass of the electron, 9.1 times 10 to the minus 31 kilograms. And then finally, the frequency we calculated here, 2.066 times 10 to the 16 hertz. We'll have to square that. And when we do, what do we get? We get 1.00020. Now, if we compare this with a true value of 1.00026, you could do this. You could say, oh, well, let's do, 100 times 1.00026 minus 1.00020, all divided by 1.00026, and you would get that this is something like 0.006% different. But this, what we really should compare, right, because this had a 1 plus a number, right, really the thing we should compare, not this, but we should just compare this component here. Ignore the 1. So in that case, we're going to get 100 times, we'll get 26 minus 20 divided by 26, and that gives me a 23% error, which is still not bad for such a crude and primitive model. Okay, problem number 5. Find the electric field inside a uniformly polarized sphere of radius r and polarized in the z direction due to the bound charge on the surface of the sphere. The problem requires integration. Due to symmetry, only the component of the electric field in the direction of P will contribute to the integral. Also note this integral that you can use towards the end of the problem. All right, this is actually a rather complicated problem. We're going to use the result in the next lecture, which is why I put it on the homework. You can imagine a sphere filled with dipoles, right? They're going to induce a bound charge on the surface of the sphere. So you'll end up with positive charges and negative charges, but they're going to be concentrated more in the direction of the polarization than they would be elsewhere. So you'll have no charges over here or over down here. And so this is what makes the problem particularly difficult. It's not the same as having a uniform distribution of charges around a sphere. Also note this is a dielectric sphere and not a metallic sphere, so the field inside is not going to be 0. But let me just go into how to solve this. There are several ways to do it. This is one way. If we were solving outside the sphere, this would be a much harder problem. But since we're only interested in the field inside the sphere, it's not so bad. So let's just have a look at it. So first thing I want to do is I want to draw a convenient picture. So I'm going to redraw my sphere like this, and I'm going to consider a little band like this. So this is just a little band that goes all the way around the sphere. And I'll let this go all the way out to here and up. Okay, so this distance is r. This angle is theta. And I want to consider this little area of element here. But the distance from the center of the sphere to this point here is r cosine theta. Okay, and so now what I can do, and then our polarization direction, P, is this way. So if I'm going to call this, I made a video that derived the surface area of a sphere, and this is very similar to that. So this is like a circumference. It's the circumference of this band as a function of theta. And it's going to be 2 pi r sine theta. Because you can see this is r sine theta. So it's like a circle of radius r sine theta, and that's just the formula for the circumference of that. Also remember that the arc length is just r times theta, which implies that ds d theta is equal to r, which means that we can write a little arc length ds is equal to r d theta. Now, the bound charge density, sigma b, is just the dot product of the polarization with the normal vector. And that is just going to be, in our case, p times the cosine of theta. So this now allows us to put together a little area, dA, which is just the circumference as a function of theta, times ds, which is 2 pi r sine theta times r d theta, just replacing these two, c of theta and also ds with these, and that is equal to 2 pi r squared sine theta d theta. Okay. Now, the electric field in the direction of the polarization in this direction, right, is just going to be equal to the electric field times the cosine of theta. And so if we now consider a dE sub p, that is going to be equal to sigma sub b, the bound charge density, divided by 4 pi epsilon naught big R squared times dA, which equals p cosine of theta over 4 pi epsilon naught R squared times 2 pi R squared sine theta d theta, which we can rewrite as p over 2 epsilon naught times the cosine squared of theta times the sine of theta d theta. And so now all we have to do is just integrate this. So E sub p is going to be p over 2 epsilon naught times the integral from 0 to pi, because we're going to go from 0 up to all the way around to pi, of cosine squared theta times the sine of theta d theta. But I gave you this answer in the hint that this integral is just equal to 2/3. You can type it into any online integrator, or you can do it by hand using trig substitutions, and we'll get that this is p over 2 epsilon naught times 2/3, which is going to just be equal to p over 3 epsilon naught. And this is, of course, in the z direction. And that is the answer. And we'll use that result in the next lecture when we talk about the dielectric due to solids.